In this work, we focus on motion-driven dynamic 3D garments and propose an architecture that learns to generate realistic garment dynamics given underlying body motion sequence. Our method produces four 3D garments with consistent texture coordinates. We first learn a compact latent space of plausible garment deformations by using a regularized autoencoder that maps a static garment geometry to deformation parameters. We then train a dynamic aware encoder which maps the previous garment geometry, its motion features, and the interaction with the body to the latent space to predict the dynamic garment deformations. We train our network on a relatively short walking sequence of only 300 frames. Once trained, we test our method on new walking styles by changing the character arm spacing. As we represent the garment geometry relative to the body without any assumption on the body parameterization, we can test our network on unseen body shapes. Here we test our method by applying a different walking style of a catwalk. We test the stability of our network at predicting a long motion sequence by iterative rollout prediction for more than 1,000 frames. Note the effects arising from the interaction with the underlying body. We also further test the generalization ability of our method by testing on challenging dancing motion sequences. While our method produces plausible results, the quality improves when the method is trained on a more similar dancing motion sequence. Here we test our method on a bodysuit. We evaluate the generalization ability of the network by changing the speed of the motion at test time. Here we show a long rollout prediction of more than 1,000 frames applied to a test sequence with different character arm spacing. Our network produces 3D garment dynamics with vivid fine wrinkle details in a long rollout prediction. We also test on an unseen motion sequence of a strut walk. Here we demonstrate our method on a pleated skirt with highly dynamic deformations. At test time, we change the speed of the motion. We also evaluate on an unseen catwalk motion sequence. Instead of assigning a fixed set of skinning weights to the garment vertices, we predict per frame dynamic linear skinning weight. Dynamic blending weights help to capture more plausible deformations, especially around the unpicked regions. For unseen motion sequences, we observe that occasional collisions between the garment and the body remain unsolved. We optimize for a residual displacement map to resolve such intersections. When training our dynamic aware encoder, we introduce a constraint that if both the body and the garment preserve their current states, we should obtain a latent code equal to the previous frame. We observe that this constraint helps to capture more accurate deformations. We compare our method to recent learning-based garment deformation methods on a dress example and show that our method captures more dynamic deformations. We speculate that this is enabled by the explicit dynamic conditioning through the use of our dynamic aware encoder and the use of a flexible blending weight function. Our method provides a potential extension to handle layered garments. We provide an initial result by demonstrating results on a two-layered garment. We train a network that learns how the yellow dress deforms given the underlying body motion. We train another network for the purple skirt, treating the yellow dress as the underlying body. We believe it is very promising to further explore this direction. Thank you.